look, I'm going to start now, if that's okay, Koen. What I'd like to do is, well, we've got 10 people in at the moment, which is great. Look, I'd like to thank you all for attending here. As I say, it's a very important subject. We're talking about from NISQ to PISQ. We're very fortunate to have Professor Koen Bertels here to deliver this presentation. He is, well, he'll talk about his background, so I won't take his thread away, but Koen and I got together for a presentation, must be a year ago now, on quantum genome sequencing, and the work that Koen and Aritra, who's here at the presentation, is really magical, and it's wonderful. So look, Koen, why don't I pass over to you, and if you can take us through the presentation.
Yeah. Okay. I'll try to respect the time that you wanted me to respect. So I'll do my best.
Yeah. Just do your best.
So okay. So the title is indeed, as Iman says, quantum computing from NISQ to PISQ. Yeah. And I heard there's already some physics people listening, and that's very good. They all know, of course, what NISQ is, and I want to make sure they also understand that there is something else which is called PISQ. Very complementary. It's not a substitute at all. I want to be very clear in the start. So my personal background. And so that you know a little bit, it's not like I started reading something about quantum, let's say 1 or 2 years ago. It was basically already 8-9 years that I'm very active in the field. I was instrumental, this is about personal marketing. When I was in Delft, University of Technology, I was instrumental in making Intel land in that university in Delft, to work on now more and more semi-conducting qubits. Yeah, and actually the group that I created, which no longer really exists, when we started defining the multiple layers that we need to build a quantum accelerator, because I don't even know what a quantum computer is, but a quantum accelerator that I can understand. So that is a bit, that is my background. The core is, of course, where are we and where are we going, or should we be going? That is a bit the idea. So I will not explain all of these things, but you will remember certain words in other diagrams, like an arbiter and things like that. But I worked a lot on FPGAs as an accelerator technology, which is nothing comparable to, let's say, quantum devices. And why is everybody so enthusiastic about quantum computing? Is because of the computational power. And if I combine 2 qubits together, so every qubit has a basis state, 0, 1, or plus minus. So that's 2 to the power 2. You have 4 states, that you can actually compare in terms of the result that it's computing. If I combine 3 qubits, it's 2 to the power 3. 2 to the power 10 is 1024, and you could even go to up to 300 qubits. That gives a number that I cannot even pronounce here. But I read somewhere, and I hope it's true, that this is more than the estimated number of atoms in the known universe. So in our universe, in which we already have, I don't know, is it between 10 or 25 planets in our universe? Because these things also vary a little bit. There's one word I do want to emphasize here. I will be talking mostly about perfect qubits, not a term that I invented, but this is even what actually the quantum physics community was also doing. And even if you look at the IBM, I will mention IBM a couple of times. They have the Qiskit kind of platform, and they have a compiler. And it's only maybe 5-6 months ago that they also started compiling towards perfect qubits. And I will emphasize why that is. In any case, if you want to increase the compute power of any quantum device that you have, you simply need to add 1 qubit, just 1, because it simply doubles, from 4 to 8, 16, 32, 64. That's how the doubling really increases with the fact that it's always in the number, in the exponent that you put the number of qubits. So that is important. However, and that is the core message of today, we are not there yet, in spite of whatever companies like even Google, and Rigetti are claiming. We're absolutely not there. I give you an overview of our 8-9 years of work. So it started very simple on a whiteboard, and now it has evolved over those times, especially the last year and a half. I worked a lot with people in Leuven, but in Porto too. So I'm Belgian by nationality, yeah, but I went to Porto to also stimulate them to look at quantum computing, yeah, and Leuven is also following in that sense, yeah. So I will come back to it. I'm the second time, and maybe it'll come back a couple of times. IBM, yeah, they first didn't think about full stacks and microarchitecture and things like that, but actually this is a paper from 2017, and where it's clear that they also started building their own stack. So that simply means that the idea that we started formulating maybe 8-9 years ago, it starts really kicking on other research groups in the field. Yeah. So that is basically what wait, I have to go to the next slide again. How do I do that? Yeah, you see it. So okay. That's why I'm introducing now the PISQ kind of vision. Yeah, everybody knows NISQ, and I will come back to that later. Yeah, and so everybody in the world doing quantum computing always mentions the name NISQ. Yeah, and it's not that we don't need the physics. We absolutely need the physics, people. Yeah, I want to be very clear on that. Yeah, because we need to make physical qubits. Otherwise, we're nowhere. Yeah. But that also means we need to work on a lot of different layers, yeah, that you see here, yeah, such that we can also explore maybe the fields on which quantum will be applied. Just we need to know that all scientific fields, and this is a big statement, I know, yeah, but all scientific fields will be substantially impacted by the emergence of quantum technology. Yeah, we saw that in our own experience, yeah, on genomics, which I already presented last year, yeah, also to Eamon's channel, yeah, but we start looking at other kinds of fields too, yeah. So this is important to realize, and I will explain this thing again towards the end, where you see NISQ and PISQ that they're jointly together, yeah, and they need to again integrate themselves at some point. When? Very difficult to predict, but I think it's more in 10, 15 years, maybe it's 30 years. Yeah, I don't know about that. There's a bit of a warning also that I want to give. Yeah, that is not actually produced by me, but this is a US-based consulting company called Gartner, and I think most of you may know it. And they've been looking all over already maybe 10, 15 years on all kinds of technologies popping up. Yeah, and now I took the one from 2018 because the later I don't find immediately quantum again popping up. It's not that it's kicked out, yeah, but I don't know what their strategy is. But here it's clear. This is the part of the hype where everybody's super enthusiastic and said, yeah, we need to do that. Yeah, we put money into it and we can solve all of the problems in the world. Yeah, and then there's of course the summit that we reached. And then people realize that by none of these technologies, and these are the ones on the downside, yeah, that there's any real product coming out of it, yeah. And so I think universities, because I'm still a professor, yeah, I started already multiple companies, but so QBX is the next one, yeah. But I stay fundamentally a scientist, yeah. So universities need to cut this cycle and simply say, okay, what is the impact in 10, 15 years from now, yeah. And so that's why I added the dotted line myself. Yeah, this is not what Gartner is doing, but this is what I did in this particular graph. Yeah, and that is basically the message also that I want to bring today. Yet another time, somebody from IBM, yeah, but it's simply because IBM is a very rational company. Yeah, it may sound contradictory to some people, yeah, but they have a particular philosophy also on quantum computing, and they have quantum scientists, but they also have quantum ambassadors. Yeah, and actually in Belgium there is one. I spoke with him multiple times. Yeah, and he's already teaching, yeah, some of the IBM kind of tools to students from the University of Leuven. But the IBM has always an honest vision about things, and so there's somebody who wrote down, yeah, that maybe it will not work. Yeah, it will not work. Yeah. Now I personally, and that's a conviction. Yeah, I'm convinced that it will work, but it may take much longer. Yeah, but we have to start now. That's very clear. I want to make the link with how we developed, and we is the technology world. Yeah, transistors. Yeah, with transistors, we make everything, every classical laptop, even phones, to supercomputers, cars. Yeah, they have a lot of processors, and they're all based on transistors. Now, it was first defined in 1934. It took like 15 years before they, in Bell Labs in the US, they managed to create that into a physical implementation. And then it still took up to the 70s before we were capable of producing transistors in a very large scale form. Yeah. And then, and 10 years later, it was in the 80s. Yeah. And I was a young guy back then. Yeah. I know that I had the first computer, which was the German one. Yeah. Based on those transistors. So simply show that it takes 30, 40, 50, 60 years before we reach any kind of productivity in any technology. So what is now quantum computing? Where are we now? Yeah. Again, for those who are not familiar with it, I cannot go into the full explanation because yeah, it would take then Emo would get very nervous and say you're crazy. Yeah, and then I would be crazy if I were to do that. Yeah, but simply we classically we know in classical bits 0 or 1. It's an exclusive or. Yeah, it's an exclusive state. Yeah, and you say okay, in the quantum world we also work with 0 and 1s. Yeah, we call them quantum bits, therefore the qubit name. Yeah, and the particular notation is the bracket notation. Yeah, but I will not explain that now. But the thing is that in quantum we can work with the 0 and the 1 in superposition. Yeah, and so this is how we combine. This is the cube side, the qubit side. Yeah, which has base state 0, basis state 0, and basis state 1. And with amplitudes alpha 0 and alpha 1. Yeah, that is important. Yeah, this simply means this is also important to simply emphasize. Yeah, quantum computing is a non-deterministic way of computing because it will produce a result, but on the quantum circuit you will need to repeat it maybe 10 times, 100 times, 1,000 times, depends on how complex the circuit is. Yeah, and it's only when you repetitively do that at some point you will do measurements of your result, and the one qubit state that you measure most of the time is the correct result of your quantum algorithm. Yeah, it is in memory computing. Yeah, I will not go into those details again, but you apply logic, quantum logic on the qubit rather than bringing the qubit to a processor, do something and bring the qubit back. So it's a completely orthogonal way of doing computations. And this is also very, very important. Yeah, and on top of that, and of course the physics people will like to hear that. Yeah, engineers much less. Yeah, the quantum phenomena are analog phenomena. Yeah, and we in the quantum in the computer world we do everything digital. So we have to recombine again the digital with the analog technology, which was basically kicked out in Delft already a long time ago. Yeah, but now we have to well, I'm no longer in Delft. Then we have to reintroduce also this analog phenomenon. Yeah, so that is important. And of course, as I said, we can combine multiple qubits with each other. So 2 to the power 3, that gives us 8. So if you count these are 8 different states from 0, 0, 0 up to 1, 1, 1. And therefore we have 8 amplitudes. Yeah, here we have only 2 because we have 2 basis states. Here I have 8 basis states, so I have 8 amplitudes. Yeah, so that is why I write down here, these are the amplitudes. Yeah. Now, what is going on? People are looking indeed about how this technology is evolving. Yeah, and I already mentioned that that the paper that we wrote on the PISQ kind of idea was now recently, and that was like 2 days ago. I received an email just by accident by Ulia Karpuscu. Yeah, that the paper was accepted for IEEE Micro, the session on quantum. Yeah, so it was invited actually. Yeah, so anyway, this is not to simply put blame or thank you for her for that. Yeah, but this I found the paper when I was presenting or preparing these slides. Yeah, like these are typical overviews of what is happening in the quantum world, and you see it's always very quantum technology oriented. Yeah, and that is not because it's not important. Yes, it is important, but we don't even know which of these technologies will convene. Yeah, will dominate the market. Yeah, and they all have problems. Yeah, so that is important for us to understand. Now, everybody, especially the physics people with a background in that field, they know John Preskill. Yeah, he's a US-based physicist. And that was in 2018, so that's almost two and a half years ago. He wrote a paper in which he said, look, and he gave a talk, look, we're actually nowhere, yeah, the potential is incredible, but we still have a lot of basic challenges to overcome. So he gave a couple of recommendations, and that he summarized in this NISQ kind of ideas: noisy, intermediate scale, quantum computing. So those are the terms, that I will now quickly highlight what at least from the papers that I went through and from how I worked on it also before NISQ was even defined, what it involves. So what are people looking at? Of course, typically, and it should be on physics problem. That's why Feynman, the guy who gave a talk in the 1980s somewhere, we said, like, if we really want to understand all this superposition, this quantum phenomena, why shouldn't we build a computer based on these principles? So that bootstrapped the entire research there. So that basically involves how do electrons interact with each other or photons interact with each other and with the outside world. So that is the field of quantum electrodynamics. But there are also other kinds of physical problems. Maybe you heard that that was maybe last year, I don't know exactly anymore. The black hole was for the first time photographed by physics researchers that had like monitors or whatever devices all over the world, always looking at one particular black hole that they knew. And this is the picture that I show now here on the slide. But there are also like fundamental problems in gravity. Gravity was something that Newton maybe for the first time explained. The falling apple. Everybody knows that image. But we still need to explain what actually is the origin of gravity. Now in quantum computing, that we do hope that we get enough computational power to look at all those aspects. And so we have many technologies that are in competition with each other, and that basically shown here. That ion traps, semiconducting, NV centers, graphene, superconducting, and you see here I already barred one. Happens to be an observation. Well, no, was an idea that was pushed by Delft. It was a colleague professor there, but he was over optimistic in the results that he got with his measurements, that he could never ever produce it anymore. So that basically caused the Nature, the magazine, the journal, to ask the professor, I will not mention his name, to withdraw his papers, to simply show like, hey, there's a lot of inconsistencies, I will not call it differently, but you see, so that is what I still think will have to go on in the next 10 years, that people say, okay, it may have a potential, but I cannot not go more than 5 qubits or 10 qubits. Physical qubits I'm always talking about. So maybe, and that will purify, and only based on a couple of people. Well, I will say about that later. So another challenge is what we see here is the decoherence. So if you put the qubit in a particular state, it immediately goes down to the ground state. And that can take nanoseconds, milliseconds, seconds. There's actually an Italian linked to an Australian university, who we're working on Silicon-28. And he managed to keep a qubit alive for maybe 4 or 5 minutes. But I do remember I came across with him, I think maybe in New York, I don't know anymore. And I said, okay, well, how far away are we to getting maybe 2, 3 of those qubits? And he simply said, I don't know. I don't even know if I'm capable of doing that. So you see, there are a lot of this is the decoherence. It's going to the ground state. So if it goes not in the ground state, then you can do something useful with it. That means you can do error gates, on it. But also there we see a lot of errors popping up, and I will give numbers later on. So that is also why John Prescott, he said we should really reduce the number of qubits we're looking at. Let's try to make them qualitatively better. And yes, he is a physics, so we need to have physical qubits. Absolutely. We cannot work only on the perfect qubit kind of idea, as I'm pushing forward now. So we now know that we need around 50 physical qubits, because the supercomputers, they can emulate and simulate that. But you need so much memory, local memory, RAM, that we cannot go beyond 50. Also John Prescott said maybe 1,000 gate is good enough, because the quantum physics people are not interested in quantum algorithms, and understandable. But they say, okay, we need to see how good these qubits are. They want to do maybe up to 1,000 rotations in the Bloch sphere, and see how good or how bad they are. And so, but we discovered, and Aritra, who is also now, I think, listening today, he discovered in his PhD research on genomics that maybe we need to go up to 10,000, 20,000 gates, Yeah, maybe not on the large number of qubits, but at least on the qubits that we really understand behave in a normal way. So to summarize a little bit whatever is going on in the NISQ world, yeah, so yes, there is indeed the 50 years that we needed to build transistors. And why should we now suddenly need much less time in actually a more complicated field? Because we need to recombine analog with digital again. First, fully understand what the analog phenomena are. Yeah. Also, we need to understand what do we understand by a good qubit? Yeah. You read that also many times. Yeah. Is that more about the error rates? Yeah. The error rates in CMOS are 10 to the minus 15. I will show a table again later on. And in qubits, we are only at 10 to the minus 2. So we have billiards of differences, yeah, between the quality, yeah. And the computation errors is also kind of a problem, yeah. So we don't know who will win in the market, yeah. And again, yeah, Majoranas for me are out, yeah. It mostly will depend on companies active, yeah. And yeah, I cannot ignore Intel because yeah, they were in Delft, yeah, and they're much more now focusing on semiconducting, yeah, but they're not at the bigger numbers, yeah. IBM, Alibaba, which is a Chinese company, are very much focusing on superconducting, yeah, but there are still a lot of challenges that need to be done, yeah. But you also have in Scandinavia, they look at photonics, NV Center is more for long distance communication, yeah. So it's very, very variable, yeah, the field that people are looking at. So now, how is quantum computing related now to the world of hardware computing? Yeah, this I will skip it. I will not go too long into this one. Yeah, you see here the difference between where we are in quantum and where we are in the CMOS world. Yeah, that's between errors every 1,000 operations or every 10 billion operations. So the number of problems you need to solve in CMOS are basically negligible. Yeah, they're not neglected, but it's negligible compared to the quantum world. So what should we be focusing on? Yeah, well, I think, yeah, we should be focusing also much more at the full stack. And this is an open invitation to all universities. Yeah, in Australia, I heard somebody from Poland, from France. I'm working with 2 universities in France. Yeah, and that basically is true for all the entire world, because it will impact all of the fields. Yeah, and if you're in chemistry, you're in medicine, you do law, you do finance, you're at application level. Yeah, and engineers like us, yes, of course, we work on these layers, and we need the physics people to do this. But if we don't have good physical qubits, well, let's assume perfect qubits. That is the core of of the message that I want to bring. Yeah, and this is what I say there. So the PISQ simply stands for perfect intermediate scale quantum computing. Yeah, and so that basically means you need to look at perfect qubits. Yeah, program them and test them on a simulator. Yeah, and yeah, such that and of course there is this one limitation. Because even if we do quantum computation on classical machines, it is orthogonal to the quantum mechanical way. It is in principle it should be in memory computation, but in practice it will not be. Yeah, so just that we understand that. So what is it that QBX and me personally, from my background in Delft, yeah, so just know that everything we did for Intel, yeah, Intel demanded that everything we did was put in the public domain. Yeah, so all papers, yeah, is on archive. Yeah, of course, many of them were published now in conferences and journals. Yeah, but the tools that we have were also shared in the public domain. So we simply took a copy of what we developed ourselves, put it into a GitHub of QBX. Yeah, and then we start working on that particular thing. So I'm going to show you now what the content is of this publicly available thing. Yeah, this is what we did, let's say in the QTech kind of environment. Yeah, and we had a compiler solution. Yeah, to go from this quantum assembler, the common quantum assembler, to an executable quantum assembler. Yeah, but now with QBX, yeah, we're more into this, and that is also an open invitation to universities and actually companies. Yeah, if they want to investigate what quantum will mean for their company, yeah, it has nothing to do with quantum mechanics as such, but it will have to do with the algorithms that we will be be formulating to create a solution. Yeah. So we are more this. So we are working. Yeah, we of course have a version of Genomics here. Yeah, we have our own programming language. So Imran Ashraf, yeah, who did his PhD with me in Delft, who is now professor in Pakistan, is one of the co-founders of QBX, together with Aritra Sarkar. Yeah, so so we need to work on the microarchitecture. We need to work again on route and map, and we developed also up to now our own simulator. Yeah, so we have to see, yeah, what needs to be changed in all these layers. Yeah, that is the substantial impact, research impact. So these are the possible domains. Yeah, I could add maybe 50 more. Yeah, but I'm simply highlighting the ones that we're going to be working on in QBX. This is already given. Yeah, we are quite far in the genomics part, and actually we start expanding it now to other fields. Yeah, could be cryptography. Yeah, could be optimizations. Yeah, but we also start working now on chemistry. Yeah, chemistry is a field that is very heavily dominated by quantum phenomena. Electrons, yeah, for instance, interact with atoms and with other electrons, and atoms with atoms and things like that, yeah, to make molecules. Yeah, so I have a lady now, Tamara Sarak. Yeah, I don't know whether she's there. I invited her also to maybe come join and listen to this presentation. She has a PhD in chemistry, and she will be responsible within QBX for all of the quantum applications in the chemistry domain. Yeah, and so I'm now I already hired actually an Iranian student also to collaborate with her, and as we get more money from our investor from Malaysia and Singapore, not from Europe, but very clear, yeah, then we will hire, of course, more people to work on those aspects. Yeah, so these are the two things that we now work on. Yeah, this is a microarchitecture. I will not go into the details. Yeah, but this is simply the one that we used for in the Intel context. Yeah, for superconducting, yeah, and semiconducting. But semiconducting with 1 qubit. So trust me, that's not very complicated to manage. Yeah, we went to 17 superconducting qubits, and now we're already at 56. Yeah, but I'm no longer involved in that kind of research. Yeah, and it's and again, it's very promising. Yeah, but I want to do also some other things. So that is, for instance, the microarchitecture, no, the quantum accelerator structure. And you see here we have our simulator, the QBSim, yeah, and we have the qubit address table, but we also need to have the amplitudes. Yeah, and I will come back to that later, the amplitudes. Yeah, so concretely, yeah, this is the list of topics that we find are very relevant for and are open invitations for everybody to look at. Yeah. And of course, we do hope that many companies, but especially universities, will start looking at applications, what the impact is of quantum, what are potential quantum algorithms in I'm not talking about physics now, but because I already did that, yeah, but in chemistry, can be in law, in finance, in medicine and things like that. Yeah. So I will quickly go here. Yeah. Again, this is a slide I showed last year too, Iman. Yeah, you must have recognized it. Yeah. So these are the different steps that you need in order to get a solution for mapping, let's say, short reads of the genome, short reads, yeah, and to map it onto the very big one. So I cannot show that on the screen because we have billions of components, and then I think we're now at 150 to 250 are short reads. Yeah, so this is an example, a much smaller example. Yeah, but this is definitely something that we want to look at, and that you can do for medicine. Yeah, for analysis, yeah, medical diseases and things like that. Yeah, this is what we will start doing, working on with Tamara Sarak. Yeah, that is on chemistry. Yeah, and again, you see here the theoretical models, but there's also the experimental model. Yeah, so this is let's say the theoretical model on a drawing. Yeah, but once you start implementing it in an experimental way, yeah, it may interact with the environment, with other kinds of components that are close to the molecule that you're looking at, or other kinds of devices that you want to build. Yeah, so this is still for me unknown. Yeah, but I'm sure that Tamara and her team, they will make substantial progress in that. Yeah. So the second topic, yeah, I just highlighted here the ones in red and in green. the ones that we know we need to modify and expand. Yeah, so I will not go too far away in that, because yeah, I'm already at 44 minutes, so Eamon gets very nervous when I go too close to the final amount of time. Yeah, the gate sets, yeah, the quantum operations. This is something that I took from the slides that Aritra has made on his work. So this is what he thinks should be done, yeah, for the genome sequencing, and this also for the genome sequencing, but we have to translate it into the current universal gate set. Yeah, so that is then this is translated into this part basically. Yeah, and this blue thing is translated into that one. Yeah, again, this opens up the possibilities to make languages richer, the kind of quantum operations richer, such that it becomes more effective for companies to look at. Yeah, of course, that needs to be supported by the language. So we have Imran Ashraf, yeah, who has been very instrumental in the compiler and also in the simulator. So now we're working here with perfect qubits in the virtual world. Yeah, well, and that may become illogical. Yeah, so again, it needs to be 2 qubit together to do a 2 qubit operation. The physics people are still here, yeah, bottom right, yeah, and they need to move up, yeah, and we need to move down, such that maybe somewhere in between here, we can start combining again the technologies again with the reasoning and the algorithms that we have. Yeah, parallelization, yeah, it is. Yeah, I will simply mention actually this. We have implicit parallelization in the quantum way. Yeah, if you execute the quantum circuit, then you have, let's say, five qubits. Yeah, and you fully entangle them, and you have maybe 10 qubit, 10 quantum gates. Yeah, you create a very open, a very multidimensional world of all of these combined combinations. So 2 to the power n, so 2 to the power 3 gives us n 8 dimensions, and they execute all of these quantum circuits in those 8 dimensions at the same time in parallel. So we get massive parallelization actually in the quantum mechanical world. Yeah, not a single physicist can know how that really works. Yeah, because and that's not me saying it, that's Vazirani. Yeah, from California, who makes that particular claim. But I do believe I never really understood what is going on in the quantum mechanical world. Now, if you want to move to classical machines, we need to do that we need to parallelize in an explicit way. We know parallelization. Yeah, you need to have a different path for all of the ways that you need to combine these qubits. Yeah, again, I will and here I will mention that we discovered that we need to go maybe 10,000, 20,000 gates. So we need to automate that process of the parallelization. And that's something that I started doing now with a colleague in Porto. Yeah. So this is a way to represent it. So this is the starting point, and then you go all the way here, and this is one possible solution, and this is another possible solution. So you can go to n possible solutions, yeah, of all the paths that you have in your tree. Yeah, so this is a way that you can combine, let's say on a supercomputer, you can combine all of the outcomes of the quantum circuit. Yeah, and then you can assess, you can still and what is interesting is that you do get the amplitudes, yeah, with the qubit computations, yeah, which you do not get in the quantum physical world. Yeah, so that makes it even more difficult. Yeah, because you need to parallelize the amplitudes that you can translate into a probability, and once you measure the different outcomes, there is one that will have the highest frequency of being measured, and that is the correct solution of your quantum circuit. Yeah, so we can do something similar in using supercomputers. Yeah, because we still need to discover, yeah, what actually the impact is of quantum chemistry, the quantum on chemistry theory, yeah, or quantum on, let's say, financial theory and so on. Yeah, so that is why it's important to make such a link. Yeah, the same idea goes there. Now this is a bit of this is a different way in which I really show the parallel structure of a quantum circuit. Yeah, and I want to emphasize again with these arrows, is bidirectional. Yeah, so quantum mechanics goes from left to right, but can also go from right to left. Yeah, so which we do not have in the classical hardware. Yeah, it always goes in let's say in a forward way. It's very difficult. It's actually impossible to go in a backward way. This is not true in the quantum physical world. So how many qubits do we need at each phase in a quantum circuit? Yeah, so every vertical line here, this is a phase this is a phase, this is a phase, and so on. Yeah, and the number of qubits that we need may vary. Yeah, so we do see that the number of qubits that we have in the beginning and at the end is exactly the same. Yeah, so the size of those graphs is exactly the same, but we can go from left to right or right to left. Yeah, that's why there's a bidirectionality, yeah, which is extremely challenging in the quantum mechanics world. Yeah, and that we need to also emulate in a decent way on classical machines. Yeah, so here we do need maybe 50 qubits, 500 qubits. Yeah, we read papers about millions or billions of qubits. Yeah, that is very, very far away. Yeah, but if we're at perfect qubits and we use classical machines and we do correct parallelization and we really reason about those concepts, then maybe it really becomes possible to make a substantial step forward in quantum computing. So that basically means the RAM is extremely important. Yeah, it's not the number of processors that we need. These are huge memories that we need. Yeah, and I simply show here that, and maybe I'm wrong. I need to be updated by people from the supercomputing world. But if you need petabytes, it's 10 to the power 15 or zettabytes. I don't even think there's a zettabyte supercomputer these days around. Yeah, it's 10 to the power 21. Yeah, and these are all bytes. Yeah. So we really need a huge amounts of memory, yeah, on which we can compute, and we know that supercomputers are limited to 50 physical qubits that we can superimpose and fully entangle. Yeah, so we have to be aware that maybe if we really want to do something useful, we need to combine maybe multiple supercomputers like I show here. Yeah, and maybe that's possible. Well, there are many. I think even Switzerland had like 20 supercomputers in a small country like Switzerland. So there are definitely more supercomputers around than we think. But we need, of course, collaboration with Amazon, with Google, IBM, and to combine them in a particular way, such that we can put our microarchitectural and the full stack on those supercomputers and have qubits routed in between these devices. Yeah, to go to the next step in the quantum circuit. Yeah. So there's one more thing that we will also start to look at. This is an animation that we made maybe 6-7 years ago, yeah, for the Intel collaboration, and that shows that maybe you need in the quantum physical world 2 qubits need to be close to each other to do a 2-qubit operation. Yeah, and so you need to move these qubits around on the surface that you see here. Yeah, to do either a swap, a CNOT, a single qubit, yeah, or when it's gray, they're inactive. Yeah, but that's how you see the routing and the mapping is clearly a very challenging problem in the quantum world. Yeah, and here you simply see the emergence if you plot the frequency at which. So red means, yeah, that this is a different color than this one, but very frequently interacting. Yeah, dark blue it's not interacting at all. Yeah, so this really gives an indication that the spatial locality of qubits is very important. Yeah, so again we can yeah, I will now move towards the conclusion. Yeah, so it's clear, and this is a slide that Aritra made. Yeah, and to which I added now PISQ. Yeah, the PISQ idea is basically, well, we have to look at the different fields. Yeah, try to come up with the quantum algorithms. Yeah, have a circuit description and do then also a functional simulation. Yeah, and we will need to move at some point. Yeah, that's what this arrow means. Again, to fault-tolerant quantum computing, because we cannot imagine that the qubits will be as good as the CMOS transistors. Yeah, but why not try to reach -7, -8, -9? Yeah, maybe then it becomes already very, very good to simulate that. Yeah, and then the quantum physics people, they also have to solve all of their very challenging problems, yeah, such that at some point we can combine again, yeah, and come to, let's say, the fault-tolerant quantum computing. Yeah, so this is how I see it. This is the PISQ vision, yeah, and this is where the NISQ resides. Yeah, so it's very complementary. PISQ does not want to be at all the substitution, yeah, but it's simply a way to do something very meaningful, yeah, because so many scientific fields will be affected by quantum computing, yeah, and we still need to wait and collaborate, of course, with the physics people, which I did also 5-6 years, yeah, before they're capable of producing good qubits, and then we can really start combining computational devices that are useful for any fields. So this is my last slide. I will not repeat it because I already explained it, I think, enough. So thank you very much for your attention. If you're interested in the two papers that we recently wrote, yeah, quantum computing from NISQ to PISQ, yeah, here I put the archive link. I checked it this morning. It's still there. Yeah, and also the quantum computing roadmap, yeah, is also still on archive. This will be now published by IEEE Micro, and I tend to integrate also the PISQ idea into the roadmap such that we have one standard technology that describes, at least for people with a PISQ kind of background, yeah, what it is that is available and what they should be doing. So thank you very much.
Well, thank you very much, Koen. That was excellent. Great to see, you know, you're actually using perfect qubits in what you're doing, and I think that's wonderful. Now, please post your questions in the chat. I have one here from Carol. How is PISQ different from the quantum information research and algorithms which assume perfect qubits as well? Is it the focus on the architecture layers and or better quantum simulators? Or is it more a revival of the focus on perfect qubits?
Well, as I said, there are too many people that claim too many things. Yeah, I had a colleague from a good university in the United States, yeah, who gave a presentation that was in the Porto context, and but he was so enthusiastic that he solved basically all of the problems with this compiler. And I said, but look, I know you're talking about superconducting, but what about CMOS conducting? Yeah, we do everything. And then I know, like, okay, there's something strange, yeah. So the PISQ is more a way to say, look, a lot of people are indeed doing quantum relevant research, but it's better to give it kind of a label, yeah. Everybody in the world is now pretending to do this kind of research, even though they're at the very high level, at the algorithm level, or working on a programming language that has nothing to do with NISQ per se. Yeah, so that's why I decided we better give it a name such that it's very clear that I showed now this graph again. Either you're here, yeah, and you don't really care whether it's ion traps or whether it's semiconducting or a graphene qubit chip, yeah, you don't care, but you're more interested, let's say, about what your company is doing or what the society needs, yeah. And so that is for me the reason why, yeah, I called the NISQ alternative, well, additional, yeah, is PISQ, yeah. And it's not that I pretend to have invented the word perfect qubit, because no, that already was done by other people. Yeah, and of course, quantum information theory, yes, everything is much more maybe linked to the PISQ kind of idea rather than the NISQ idea. Yeah, that's basically my answer.
Okay, another question, Koen. What if a quantum applications developer is already developing in a NISQ? What would it take them? How much would they have to change their modus operandi to move to a PISQ environment?
Yeah, I'll show you now another graph that I showed here. Yeah, so whenever you go into NISQ, yeah, this NISQ simply means this is the environment in which you're working. Yeah, so it depends on what kind of physical qubit you're targeting. Yeah, but we see here, we do everything in sequasm, yeah, which we did also back then for Intel. Yeah, and then when Intel said, okay, now you need to control the one semiconducting qubit or the n superconducting qubits, yeah, we made the translations from C to E, yeah, and C means it's common, and E means executable. And trust me, you have to take all of the low level analog but low level electronics constraints into account. Yeah, so it's not like it's a simple translation. We know how to do it for relatively small systems. Yeah, we still have a lot of discovery to do. Yeah, and that is what Imran Ashraf in QBX, yeah, and in Pakistan will work on. So it's not like, so once you're in NISQ, maybe there will be certain differences in the microarchitecture. Yeah, maybe in the route and map, yeah, because the topology that IBM is using has a very strict kind of layout, yeah, and maybe you will have a completely different layout if you go to ion traps. So again, the routing in the map at the higher level, what we do here can be general enough, yeah, can be abstracted away from a particular physical implementation, but you will need to make the move at some point with specific routing and mapping constraints for this particular kind of technology. Yeah, so there are substantial differences, but we first need to understand what the routing and the mapping in general is before we can apply it on any kind of particular kind of physical topology.
Excellent. Okay. Now another question is, do you have any idea or grasp on speed times? You know, quantum benchmarking on the two systems. I know it's very difficult to compare, but you've got pros and cons with both, like the parallelization system that you mentioned that really perfect qubits on a supercomputer can't really do because they can't go forwards and backwards. So what is the sort of speed differences between them?
That is, I think, the question that is maybe the most difficult to answer. Yeah, because we've been looking, that's what I did at least for years in Delft, relatively small kinds of quantum circuits, random circuits. Yeah, they go in all kinds of directions, but once you go into, let's say, Grover or other kinds of algorithms, they're very directed. They go to a particular goal, and so how can you combine a random circuit, yeah, with a targeted kind of application circuits, quantum circuit? So are we talking about seconds, minutes, months, years? Yeah, there are too many claims. Google pretended last year also that it broke the quantum, I don't know anymore how they call it, this quantum supremacy. Yeah, but then IBM replied for the same thing. No, this is not true. Yeah, so if even the physics people don't agree on that, yeah, then I cannot say anything meaningful about that. So I do know that the principle of quantum computing is extremely parallel and will go extremely fast. But how much fast that will be, I have absolutely no idea. Yeah, because there's so many low-level electronics involved. Yeah, if you're doing superconducting, yeah, you have to create a superconducting qubit. Yeah, that's a millikelvin. So 0 Kelvin is basically absolute minus 273 point something Celsius. Yeah, so millikelvin is very, very close to the absolute zero in Kelvin. Yeah, so how much faster, how many can we compute if we need 10 million? I have no idea if that's even possible. Yeah, so that's where the big challenges are for the physics people, and I do hope that we can keep them motivated. That though they say it's never going to happen, yeah, maybe in 100 years we will be able to do it. Yeah, but I think it may take another 10, 15 years. I believe that it will happen. Yeah, but in much smaller amounts. So, but how much faster it will be, and yeah, the bidirectionality actually on a classical machine is also possible, because if my algorithm is bidirectional, yeah, in sense of qubits, yes, I can go from back till the beginning, or from the beginning to the back. I can do that. Yeah, it's a logical kind of concept. So again, that means that do I have enough memory in a supercomputer? That is for me the big challenge. If I'm limited to 50, 60, yeah, even in genomics, we know that for a virus, we need 110 qubits. For a human being, we need 150 qubits. Yeah, so that means we need a lot of supercomputers that can be interconnected to solve one particular problem. Yeah, so it's a difficult question. Yeah, so I cannot give, let's say, oh, this is the solution. Yeah, it's still open science. Yeah, so but we have to try, and I think PISQ is a very good way of trying to discover that.
Yes, thank you for that, Koen. Now, I don't know whether this question is outside your scope, but is there a difference between, you've spoken exclusively about quantum gate-based approach. What about quantum annealing? Is there a difference you know, between using NISQ and PISQ with a quantum annealing type situation or a quantum
Yeah.
gate based.
Yeah, I did look at that, yeah, and actually there's only basically one company in the world. It's a Canadian company, D-Wave, yeah, and they're very respected, yeah, and so they claim to have more than 2,000 or 3,000 qubits. No, they never mention what kind of qubits they are, yeah. So it's very, yeah, it's a big claim. It's a big claim, and they only work on optimization. That is true. Yeah, so but I looked at those algorithms also at some point, and I spoke with people from D-Wave, but that was in Germany, and then I said like, okay, they themselves they don't know, yeah, and I understand that because yeah, that you cannot reveal all of the secrets of the company to all of the employees, yeah, but I said like, no, this is one a very meaningful way, but it's one specific kind of technology. Nobody really knows what those qubits are. Nobody really knows what these algorithms are. Yeah, optimization. Yeah, everybody does optimization in the world. Yeah, so for me, it is clearly it will be part of, let's say, the offering, worldwide offering. But what exactly it is, it's a black box, literally a black box. Nobody really knows, except of course the D-Wave people. That's it.
Yes, exactly. Now, if you've got any more questions, anybody, just you can actually, I think you can unmute yourself if you so wish, or you can pop them in the chat room. I think this is a very important area because at the moment, correct me if I'm wrong, Koen, but in the NISQ, if you're creating algorithms, you don't know which is the right one, do you? You don't know for sure how accurate what you're putting in is coming out.
Yeah, that's why there's this concept of oracles in quantum. Yeah, so that it's kind of a black box. You know, in Oracle, that's actually from the Greeks basically. Yeah, they didn't know. They asked the Oracle, yeah, what do you think will happen? Yeah, so that's what we also think. Yeah, that some people say, okay, we do something, but we don't really know what it's doing. Yeah, but it's like a couple of things, gates mixed with each other, and they expect they will then check the outcome of the Oracle. Yeah, so that's why it's an important tool, yeah, that we need to develop even much more. How to build an oracle, how to test an oracle, yeah, how to change an oracle, yeah, because these are all things that we need for really profound understanding of the quantum mechanical aspects of any kind of field that we're looking at, yeah, be it chemistry, be it medicine, yeah, or even finance, yeah. So it's very difficult how to predict. Yeah, but oracles, yeah, they're an inherent part of any quantum circuit.
Yes, I like the way you mentioned that during the presentation. I get asked a lot when I'm doing training or on my courses when I talk about the fact that you can't measure a qubit because it collapses to 0 or 1 due to the collapse of the wave function down to the double slit experiment and all the different interpretations of why it's collapsing. But irrespective of that, it actually collapses. So people say, you know, what good is it? And you mentioned like the quantum tomography where you have to run the program 1,000,000 times and then it will throw up the solution. But it's all very all quantum computers are just based on that probability, aren't they?
Yeah, that's true. So it says that's why I say it's non-deterministic computing.
Yes.
Yeah, so you have to execute it multiple times, do the measurement of these multiple times, and how much that multiple times is. Yeah, that's also something that needs research. Yeah, is it like number of qubits and then times 10? Is it the complexity of all the qubits together times a number? Yeah, that is something that we don't really know yet, but that will happen. Yeah, that's why we need many more people to look at those aspects, and that I think is more of the PISQ kind of idea than the NISQ idea.
I totally agree with you. Just in your estimation, because you know these things, fault-tolerant computing, which is quantum computing, which is where we all want to get to, where we need to get to, where we will get to, because we're talking the word I in NISQ and PISQ as intermediates, where this is a stopgap solution. But how far away do you, I know it's an impossible question to answer, but how far away do you think fault-tolerant computers are, quantum computers?
Well, we worked a lot. Actually, the first couple of years in Delft, we worked on fault-tolerant quantum computing. Yeah, I had four people actually graduated with me. Yeah, and they were always related in some way to this fault tolerance, and that was always based on we make surface code, which is a logical qubit consisting up to, in principle, theoretically, up to 49 physical qubits. Yeah, but so we did that, but then I saw like there's no real impact. I cannot make any innovation there, and that is the reason why I changed. So fault tolerant, yeah, that's why I said here we will move again to fault tolerant, yeah, and the NISQ is fault tolerant. We'll have to reintroduce those things, and then we get to a real implementation of the number of qubits that behave in a good scalable way and produce good results. Yeah, and that's an estimate. I think it's going to be 10, 15 years away, maybe 20. I don't know. Yeah, but yeah. Not 5. That is what my personal opinion is.
No, and there's no way to get around the RAM limitation on PISQ either, is there?
Sorry, what?
Well, the limiting factor with PISQ is the RAM that is needed. Yeah. You mentioned zettabytes, which I think I agree with you is way beyond anything we have at the moment. And I'm not an expert in that area, so I hope I'm not wrong. But we have a few connections who are using supercomputers and they can verify it. But the limitation for PISQ is the RAM requirement. Is there any way that we can, make a virtual RAM type thing or get around the RAM by making the computation work in a different way?
Well, we have wait, I'll show you this this slide again. Yeah, no, it's running away. This one. Yeah, we have to investigate how many qubits are alive at any phase, yeah, any step in any quantum circuit, and this the maximum number here, yeah, it's this, which is this one, that will determine how much memory we really need in supercomputers to run the experiment, yeah, and if it's and we do hope, of course, it's still going to be relevant for any of the problems that we're looking at, yeah, but. So this is something that is still needs to be investigated. Maybe something that we will do in Leuven, but I don't even know now, yeah, how to do that, yeah. So we can run, let's say, 20,000 gates in genomics, and then count how many qubits are alive, have a particular value in its basis state, yeah. But that will give us to understand what the relation is of number of qubits in memory that they will need to represent in a classical machine.
Yes, excellent. I've noticed a couple of people just come in who have probably got the timing wrong for Perth, Western Australia, because in point of fact, we've just come to the end of the presentation. I'm thinking of you, Jamie, who's very knowledgeable in this area. I don't know whether you're just unavoidably late or whatever, but we actually are concluding the presentation. I don't know whether you had a question in mind that you would... by the way, it is being recorded, so I'll send a recording out to everybody, and maybe a copy of your slides as well, Koen, is that okay?
Yes, of course. I sent you the PDF version of the slides, so yeah, you're free to share it. Yeah.
Yeah, no, I can take care of that. Jamie, did you have a question that you'd sort of wanted answered?
Not specifically. I'm just listening in right now. You meant thank you, though.
Right. Okay. Yeah. Terrific. I just look. You can follow up with me later, anytime, as you know. But we're actually just finished now. We've I don't know whether you got the timing wrong with Australian Western Standard Time. I'm used to it in Perth. I'm the only one in Perth does these things, and people constantly, either come in and 2 hours early or leave 2 hours late. But look, I'd really like to thank, now if there's no more questions, if anybody's got a question, now is the time. Yeah, it's probably very early over there, Jamie, so, normally I'm on the receiving end. Lots of the presentations I want to go to like 4 or 5 in the morning. But look, a big thank you to Koen. I think you've answered that, you've outlined the issues brilliantly. I mean, this is a real, it makes a real difference for where we are now. Where we are now, are we doing things the best way so that we can improve all of our quantum algorithms? And I hope this will generate some questions out there for any quantum developer, because this is an issue, would you agree, Koen, that should be in the forefront of their minds?
Yeah, that is the goal. We wrote this paper, Arita Imre and me, and to really give it a label that people will remember. Yeah, and then because it's an eye opener, I think, for so many fields that are not looking at all at quantum. But if ever these devices will make it, and I'm sure they will, yeah, it will impact all of the scientific fields that every university or even company is involved in. So in that sense, yeah, that is for me the most important conclusion that we need to get from my talk. And if I'm wrong, you can blame me. Yeah, but if it's correct, yeah, I do hope it's still, we still have time, yeah, to start studying. Yeah, but we need to put young motivated people to do a PhD, young professors to start their research into that line.
Look, absolutely, it's all about the generation coming through, and getting them to make the most out of what they're doing, which has been the case for since day dot. So again, I'd like to thank you, Koen. We'll finish it now. We'll finish it here.
Okay.
If anybody has any questions, you can email me. And as I say, I'll be sending a copy of the recording and the slides to everybody who's registered through the event registration. Thank you, Koen, and no doubt you and I will talk soon, and very illuminating.
Okay, thank you very much.